The name of this video is Energy Continuous Revisited. We know that the electrostatic energy for a continuous charge distribution is given by UE equal 1/2 the volume integral in a superregion capital omega infinite, which is the entire universe, or our entire lab, if that's sufficient, of rho at point capital Q times V at point capital Q times dr capital Q cubed. The reason why we need to consider the entire universe with the meaning I gave you earlier of universe, the lab could be sufficient, is because we want to find the electrostatic energy everywhere in space. The electrostatic energy, if I have a point-like charged particle in space, and that's the only particle I have in the entire universe, the electric field extends all the way to infinite. Okay, so I have an infinite extension, and so I need to, in order to catch all the energy associated with that system, I need to integrate over the entire universe. If I integrate over a subset, I obtain something less than the entire energy. That is why we must integrate over the entire universe. If we do that, we can attempt to now find an equivalent expression for the electrostatic energy by using some vector calculus. So every time we use vector calculus, we need to keep in mind that actually the expression we get after using vector calculus expressions is going to be less general than the one we began with. And why is that? Because we need to impose conditions, vector calculus conditions. So in this case, let us hypothesize, as always, that rho is a continuous function in the entire region capital omega infinite, in the entire universe. So the volumetric charge density rho is a continuous function and is also a limited function. That is, actually, rho is different than 0 only for each point capital Q in a region capital omega which is smaller than capital omega infinite. This means limited, okay? So I have a little object and I'm integrating over the entire infinite, but there is vacuum almost everywhere except where the little object is located. All right. With that in mind, we know that we can use Maxwell's equations for the electrostatic field. In particular, we know that Gauss's theorem can be written in differential form case 1. The divergence of E is equal to rho over epsilon naught. From this, it follows that rho can be written as epsilon naught divergence of E. This quantity is the quantity we want to substitute in this expression up here for rho. We also know that since the curl of E is equal to 0 and we are always in a compact or simply connected domain, we also know that from the rotational property of the electrostatic field, it follows that E is conservative, so we can write it as the gradient of capital V. These are our Maxwell equations. This is equivalent to the rotational property. So these are our Maxwell's equations for the electrostatic field, okay? Under these conditions, so we are limiting ourselves to these conditions, okay? So remember that. This is a very general expression. We can always use it. If we limit ourselves to this subset of conditions, then we can use case 1, the differential form, and that's what we get. But it's critical to remember that that's what we are doing here. We will give an example to show the importance of that condition. All right, so now we can substitute this expression up here, and what do we obtain? We obtain simply the integral of epsilon naught, the divergence of E times a scalar function. From vector calculus, you should know that the divergence, which is our operator here of interest, of a scalar function small f, scalar, times a vector function capital A vector, is similar to the derivative of the product of functions and normal regular typical derivative. So first we do not derive f, and we derive a. We need to get a scalar, so it has to be the divergence of a. And then we choose to derive f and not a, so we need to still have a scalar. So a has to be dotted scalar product with a vector. The only vector we can get out of a scalar is the gradient of f. Okay, so from this, it follows that here, note that we have, when we substitute this expression up here, we have a constant, the divergence of it times a scalar. So we have a scalar times the divergence of a vector. Okay, so this is what we basically have up here after doing all these substitutions. Okay, so let us find, in fact, this expression f, divergence of A. Let's explicitly find it. So we bring this to the other side, and we obtain that this is equal to the divergence of the structure f times A, close parentheses, minus A dotted with the gradient of f. Now we can do a simple mapping where we know that f is equal to capital V, whereas A is equal to E vector, the electrostatic field. By doing so, we can substitute this expression into this integral, keeping in mind this expression here, and therefore we obtain here that UE, the electrostatic energy, is given by 1/2 the integral, two terms, the volume integral on the entire universe, capital omega infinite, so the whole space where we want to capture our energy. And then we have the first part of the expression, which is the divergence of FA, which in our case, from our mapping, this is nothing but the divergence of B, capital B scalar times capital E vector, the electrostatic field. Okay? This has to be integrated. So now, remember, we are substituting all the integrand, okay? So by means of this substitution. So we obtain this, which has to be integrated over the R cube. Let's keep our cube not to forget. So that's the first term. The second term is still 1/2. So let's explicitly write it again, not to forget it. Minus 1/2. And of course, we need to remember also that there is an epsilon naught in front of everything, because we substitute the rho with epsilon naught divergence, okay? So we need to remember that. Similarly here, there is an epsilon naught, the volume integral on the entire universe, capital omega infinite, of this other expression, which is E with the minus sign, dotted with the gradient of capital B, again in the R cube. Excellent. So now this is a very typical proof that we will do in many different cases also in 342. So let's try to understand this well, okay? So let's remind ourselves what we've done. We substitute the rho with epsilon naught divergence of E. That's why there is epsilon naught everywhere. Divergence of E times the scalar B can be rewritten by means of this vector calculus identity. That's why there is a minus sign here. So now, let's first begin with the first integral. So let's begin with integral 1. Okay, so this is the integral of interest. This is very simple. We'll do it at the end. It's very simple. This one is a little bit more complicated. But let's look at this. We have the volume integral of the divergence of a quantity, which is a vector, V times E, the whole quantity. So we can use the divergence theorem. From the divergence theorem, what we obtain here, this first integral becomes 1/2 epsilon naught the volume integral becomes the surface integral on the boundary capital sigma infinite of the entire universe. The divergence becomes simply V, the argument of the divergence, times vector E, dotted with NdA. The flux, so we are computing across capital sigma infinite, which is the boundary of the entire universe, the flux of a quantity, V scalar, so it's a prefactor of V dot NdA. So the quantity is VE. The second integral we will do it later. Now, note that we could choose pretty much whatever we want for this capital sigma infinite, okay? So if this is our regional space capital omega, where actually there is a rho associated with it different than 0, rho is equal to 0 everywhere outside here is different than 0, outside this regional space capital omega. So we could go all the way to infinite by means of any boundary we want. This could be our boundary capital sigma infinite. But as a matter of fact, we can choose a simpler boundary, which goes all the way to infinite. And this boundary could be a sphere. So we can use capital sigma to be an infinite sphere, which means it's a sphere with a radius r, capital R, that goes to plus infinite. We can use such a sphere, okay, with the center somewhere here, with this radius capital R, which goes all the way to infinite. Since we are going to infinite, we can choose the simplest infinite boundary that we can choose. We could choose an infinite cube, but that's more complicated. Let's choose an infinite sphere. Why is that? Because in this case, we can represent this sphere in a spherical coordinate system R. This is the origin, and of course there is also a var phi and a theta, which I'm not going to sketch here. So it's a spherical coordinate system, okay? If we do that, we can re-express this integral here simply as 1/2 epsilon naught. Now we are doing the integral right on the boundary, okay? So we need to use an infinitesimal area element. So we do the integral between 0 and 2 pi in d var phi, integral between 0 and pi d theta sine theta. Let's keep r a generic r for now. So small r squared, that's our infinitesimal element. Okay, then we need to do the limit to infinite. So r squared, okay, so this is our r squared, d theta, sin theta, d phi, that's our infinitesimal area element. This, we didn't forget it. Times v times e dot nda, which let's keep it as such for now. And dA, we already consider it in this fashion here. Okay, so now the next thing we need to do, we need to calculate this quantity in the limit for small r that goes to plus infinite. So eventually, this small r becomes the radius capital R, which is infinite, of this sphere. Okay, so if we do that, we know that when we look at this bulb of matter, which is in capital omega, from infinite distance, it looks like if it were from very far away. It looks very far away as if it were a point-like charge concentrated in the origin O. So in this limit, we know, we can calculate already this first part of the integral. So we obtain 1/2 epsilon naught times 2 pi times 2, which is 4 pi. Let's remember here what we have. Now, V, very far away, the far potential is going to be approximately, so this is far potential. The far potential goes as the total charge, which is rho integrated over this volume associated with capital omega, so let's call it Q. So it goes as Q, of course, 1/4 pi epsilon naught, so it goes as Q divided by R, whereas in the far scenario, E vector, is proportional with a direction which is same as n, so it's proportional to n q divided by r squared. Okay, so n dot n gives us a 1, so in the limit we obtain 1/2 epsilon naught, 2 pi times 2, which is this integral, which is 4 pi, this integral here. Then we obtain 1/4 pi epsilon naught, both for b in the far case and e, so we obtain 1/4 pi epsilon naught quantity square. Then we obtain q square. One q is from V, one q is from E. Then we obtain 1 over r for B, 1 over r square for E, and this r square from the infinitesimal element, that is, these two r squared go away. So now these are all constants. 1 over r for r which goes to infinite is equal to exactly 0, which means we can state that this integral does not contribute to the final electrostatic energy. And again, the reason is because I push this r to become the infinite radius of this infinite sphere, which I consider for capital sigma infinite. All right. So now we need to conclude the proof here. We need to consider this other integral, which is integral 2 here. So the integral 2, it's very simple because we know that E is equal to minus the gradient of V. So minus minus is plus, gradient of V dot gradient of V is nothing but E squared. Okay, so we obtain simply E squared. Okay, so we obtain plus because of this minus sign. So again, minus minus is plus. This is gradient of V, or if I want, I can just substitute minus E instead of gradient of V and obtain the norm of E squared. Okay, plus. So the electrostatic energy, in this case, let's write down what is the second integral, which is 1/2 plus 1/2 epsilon naught, the volume integral over the entire universe infinite of E norm quantity square integrated over the entire volume dr cube. Okay, great. Now, I know that people always have a problem here. So, oh, why this one goes to 0 and this one is also an omega infinite? Why this one does not go to 0? The reason why this one is different than 0 is because here we are integrating over capital omega infinite. So we are integrating everywhere. Also, a finite distance is not only on an infinite boundary. This was only an infinite boundary. Whereas here we're integrating also a finite distance. So this one clearly is different than 0 because of that very reason. Therefore, the electrostatic energy is simply given by, in this case, UE equal 1/2 epsilon naught volume integral in the entire universe capital omega of the absolute value of E squared integrated over dr cube at cube. Okay, so that's our electrostatic energy. This encodes the same information. This result encodes exactly the very same information as this result here. They are equivalent. The only difference is that this one we obtain it using a certain conditions here, so it's more restrictive. That is, this you can always use it, and it gives always the correct result. This one you need to be careful only for case 1. So you need to be very careful when to use this expression. The reason why people like it is because from this you can define an electrostatic density, which is small u E, is called density, and this density is given by, you remove the integral, so you do basically the du over dv, and so it's simply given by 1/2 epsilon naught E squared, which again is nothing but due over dr cube, the infinitesimal volume element, q cube. Okay, this is called density, which clearly shows that the electrostatic energy is stored in the electrostatic field. This is the storage, is where the electrostatic energy is stored. It's stored in the electrostatic field. That's why this is a beautiful proof to show that it's stored in the electrostatic field, but it's less general than this expression. Okay, so to summarize this video, we wanted to revisit the concept of energy in the for continuous charge distributions. We started from the most general expression, which is up here, rho v. We use some conditions which are the same for case 1 for the Maxwell's equations. Therefore, we can use the differential form case 1 of Maxwell's equations, which are these two. This is the same as the rotational property. We can substitute Gauss's theorem into rho, and use this vector calculus identity, which allows us to split this integral in two sub-integrals, 1 and 2. The first one happens to be, we need to do it over the entire universe. By means of the divergence theorem, from a volume integral, we go to surface integral on the surface which encloses the entire universe, which we can choose to be a sphere with infinite radius. This is only calculated on that surface, so when we push in the limit that the radius of that surface to be infinite, we obtain identically 0 in that limit. Okay, and we use the concept of far field and far potential, 1 over r and 1 over r squared, because again, this object is like a point-like charge when I look at it from very far away, far potential and far field. The second expression, by means of the rotational property, conservative field, we can write it as E absolute value squared, which gives us this expression showing that the electrostatic energy is stored in E. That's it.